Welcome. Today I'll present FatPuro, our study on how fine-tuning impairs the balancedness of foundation models in long-tailed personalized federated learning. This is a joint effort, and I'll walk through the problem we identify, the method, and the empirical evidence. When we adapt foundation models like CLIP under federated long-tail data, the updates erode the balanced knowledge these models already carry. This imbalance then propagates into personalized models through parameter or feature-level fusion, and even legit adjustment cannot restore zero-shot balance. The figure illustrates the core issue. An imbalanced global model compromises personalization rather than supporting it. First, the temperature-aligned KL divergence rises during training while balancedness drops, a strong negative correlation. Second, fine-tuning improves head class accuracy but degrades tail class accuracy, so the gain is not balanced across classes. Together, these plots show that balance degradation is a persistent phenomenon during federated fine-tuning. CVPR combines two ideas: global balance training and personalized residual learning. Gradient purification keeps the global branch aligned with zero-shot balance knowledge by filtering out conflicting updates. Server aggregation stays standard, and the personalized branch learns residual corrections in logic space. The key idea is to separate balance preservation from personalization, rather than entangling them in a single feature fusion step. We define an alignment loss that measures whether a task gradient pulls the model toward or away from the balanced zero-shot prior. An orthogonal projection rule then strips the component of each task gradient that conflicts with the alignment direction. This guarantees that updates contradicting balance knowledge are removed at every step. As a result, clients can adapt to local data without breaking the zero-shot prior. For personalization, we introduce a residual branch that operates in logic space rather than feature space. The global branch is frozen and provides balanced baseline logits, while the personalized branch learns client-specific corrections. The final prediction is the additive sum of the global and personalized logits. By doing personalization as an additive correction in output space, bias does not propagate through feature fusion. We evaluate on 8 long-tailed image classification benchmarks covering natural and fine-grained domains. We compare against a broad range of federated parameter efficient fine-tuning baselines spanning prompt, LoRa, and adapter-based methods. Client heterogeneity is controlled by the Dirichlet parameter and class imbalance by the imbalance factor. We report both global and personalized accuracy broken down by many, medium, and few shot classes. All experiments use clip-fed by16 with 20 clients, 100 communication rounds, and 40% client participation. FatPro achieved the strongest performance on both global and personalized models, with the largest gains on few shot classes. It even surpasses methods that rely on explicit class priors, although our approach uses none. The gains hold consistently across prompt, LoRa, and adapter-based fine-tuning families. The accuracy curves on the right show faster convergence and higher final accuracy on the long-tail cipher benchmark. The ablation first compares gradient purification against alternative balancing strategies. Our variant best preserves the zero-shot balanced knowledge, validating the projection rule. For personalization, residual learning is compared against feature fusion alternatives, and the output space residual avoids inheriting bias. Combining both components yields gains beyond either alone, so they are genuinely synergistic. Standard methods steadily lose balancedness during training, while FatPOL stays close to the zero-shot starting level. This holds for both global and personalized models, so personalization does not come at the cost of balance. Both plots reinforce the same picture. Our method maintains higher balancedness across the entire training trajectory. Standard KL divergence conflates confidence shift with actual class bias, staying large, even on balanced data. Our temperature-aligned variant neutralizes confidence and isolates structural bias, becoming near zero on balanced data and large on long tail. The plots confirm that this metric captures genuine balance erosion rather than spurious confidence changes. The third analysis measures client drift as the distance between each client's model and the global model, because gradient purification anchors all clients to the same zero-shot reference. Cross-client drift stays small and stable. This reduced drift leads to faster convergence and better aggregation quality visible in the lower drift curve for our method. The fourth analysis shows that the global and the personalized branches are complementary, not redundant. For head classes, the global branch dominates correct predictions. For tail classes, the personalized branch contributes more, while the global branch still supplies about 20 to 25%. This confirms the design choice of combining balanced global knowledge with targeted local adaptation. The fifth analysis explains why gradient purification works. By visualizing the angle between the task gradient and the alignment gradient during training. For baselines, the angle converges toward 90 degrees, meaning task optimization ignores zero-shot alignment and balance erodes. For fed PRL, the angle stays obtuse, so the conflicting component is consistently removed and updates remain balance-aware. The figure thus supports our interpretation that purification preserves alignment rather than merely slowing learning. To conclude, foundation models carry an implicit balance prior, and fine-tuning should preserve it rather than overwrite it. CVPR combines gradient purification with residual learning, a simple prior-free recipe that beats prior-based methods. We observe consistent gains across all three long-tail benchmarks and a wide range of heterogeneity settings. The take-home is simple. We use what foundation models already know instead of fighting it. Thank you for your attention. The code is open source at our project repository, and our emails are listed here for follow-up.